We're going to do now lesson 3 in volumes and surface areas, which is the surface area of cylinders, cones, and spheres. We're going to start with cylinders. First of all, I'm going to define it. A cylinder is a 3D solid with two bases that are circles. It is not a polyhedron because a polyhedron has to have polygons as bases, and these are, and faces in general, and the bases in this case are circles, not polygons. Okay, let me draw it over here. So I'm going to draw a 3D version of a circle to give it perspective, which is an oval or an ellipse, and then connect the two like that. There is my best drawing. There is my cylinder. Dotted line this one in the back. The dimensions of a cylinder, you have a radius and a height. And the height has to be perpendicular, the perpendicular distance between the two bases. This up top here is a base, and there's another one on the bottom there. Okay, this is called a right cylinder as well because it's a right angle here in the height, and if it is a right cylinder, the height is also the side length. Okay, now we're going to do surface area. To do that, we're going to create a net just like we did in the previous lessons. So I'm going to create a net of a cylinder. Net of a cylinder is a circle on the bottom and a circle on, sorry, that's the top, a circle on the bottom, both of radius r. And then you have in the middle, if you unwrap a cylinder, you actually get a rectangle. You can test it out with just a piece of paper. If you take a piece of paper, round it up like that, you will get a rectangle. Like so. The rectangle will have a height of h, right there, and it'll have a width that is the circumference of the circle that it is laying on, which is 2 pi r. There are three surfaces, 1, 2, and 3. I shall label those slightly different, 2 and 3. The surface area, therefore, of a cylinder using the net is pi r squared for one circle, plus pi r squared for the other circle, plus the area of this rectangle, which is 2 pi r h. 1, 2, and 3 surfaces. Okay, so, and by the way, when you write this formula, make sure these are separate. Pi r squared and pi r squared. Don't write it as 2 pi r squared, which I think the book might. The reason you don't do that is, first of all, this tells you it's three faces, so you have three things you're adding up. So it's a good sanity check. Plus, there's no reason you can't have, for example, a cylinder without a lid, in which case one of these is gone, but the other one's still there. So it's important to recognize it as three different faces. Okay, what are cylinders used to do? You see them everywhere. We store things in them largely. Cans in the pantry, glasses, garbage cans, things like that are all cylinders. The reason we use cylinders so frequently is two things. One is they are a good way to have a large volume with a limited surface area, which minimizes the cost and weight of an object. It's not the perfect one. The perfect one is actually a sphere, but it's a good compromise, the cylinder. Again, it creates the maximum volume of this figure for a minimum of surface area. The second reason we make them and use them is they're easy to make. So if you're making a metal can, for example, you can just cut a cylinder into the middle part of the cylinder into a square like this, or a rectangle, and then you just wrap it around and you connect the piece across it. And if you look in the inside of a tin can, you'll actually see this wedge here welded together. Okay, I'm going to give a couple problems on this now. So I'm going to erase everything but the picture. And put some numbers on it. So I'm going to make the radius, in this case, 3 feet, and the height 4 feet. And I wanted you to find the surface area. So pause the video and try to do this yourselves. Okay, if you're back, surface area is simply pi r squared plus pi r squared plus pi r l. Sorry, what do I do that for? 2 pi r h, jumping ahead. 2 pi r h. In this case, pi 3 squared plus pi 3 squared plus 2 pi, radius is 3, and height is 4. So you get 9 pi plus 9 pi, plus that's 24 pi. That is, let's see, 18 plus 24, 42 pi, which as a number is 100 and 31.95 feet squared. There we go. Hopefully you got that. I did notice I didn't draw a net this time. It's always going to be a circle, circle, and a rectangle. So I didn't redraw it. If you feel comfortable and want to do that, you don't feel comfortable and want to do that, go ahead and do so. Okay, we're going to do one more. So again, I'm just going to erase this. I'm not going to erase the picture. This time, I'm going to give the surface area as 592.19 centimeters squared. And I'm going to give the radius as 6.5 centimeters. And now I want you to find the height. Okay, so try that yourselves first. Pause the video. Okay, you're back. I'm going to write an equation. Surface area equals pi r squared plus pi r squared plus 2 pi r h. And I want to solve for h. I have r there and there and there, and I have the surface area. Just to give a general formula, I'm actually going to solve it without the numbers in it first. I'm going to take the surface area. I'm going to take these 2 pi r squareds and subtract them from the surface area. And then I'm going to divide by 2 pi r on this side and this side to get h, like that. Okay, now I'm going to put some numbers in. Surface area is 592.19 minus 2 pi, r is 6.5 squared, all over 2 pi 6.5. Okay, and I'll do that in the calculator. 592.19 minus 2 pi 6.5 squared. Take that, all that, and divide it by 2 pi 6.5. And make sure you put this in parentheses, by the way, if you want to put it in a calculator. So it divides this whole thing, as opposed to just dividing the 2 and then multiplying by pi and 6.5. And you get 8. Pretty much rounded almost exactly to 8. 8 feet. And, oops, that should not have been centimeters, not feet, centimeters. Okay, and there's your height. Okay, now we're going to move on to cones. So erase the whole board here. Start a new section of your notes and write cones. Again, I'm going to do the same thing. I'm going to define it, draw it, and talk about what it's used for. So a cone is, again, a 3D solid with one circular base connected to a vertex. So let me draw that. I think everyone knows what a cone looks like. So what I'm saying is, there's my radius. This is a circle. It's connected to one point up here, which is the vertex. Again, it's not a polyhedron because it's not, the circle is not a polygon. Another couple things I need to write on here. I'm going to write the height down. So here's the height. The problem with this in this case is the height doesn't actually help us find the surface area because the height is from here to here, not here to here. So that dimension isn't going to help us. So what we actually really need is this, which is called the slant height, which is the distance from the vertex to a side of the, or to a point on the circle. And that in geometry is typically written as L. Not sure why, but it's L. So this slant height is L, this H height is the vertical height, the perpendicular height. We will use the height when we get to volume, but in this case largely we're going to use the slant height. Okay, one other piece to this side of this is called the lateral side or face or surface. That was true in the cylinder as well, I didn't point it out, but that rectangle was the lateral surface. Remember that lateral means side. So it means side, side. Maybe use lateral surface instead. Okay, so now the surface area. I'm going to draw a net. This is obviously just part of this bottom part is just a circle again of radius r. This is not obvious what happens to it. In class I usually cut a piece of paper to show this, but what this piece here looks like if you unravel it is a single sector of a circle. So it looks like this. That, and this is the center of it. This is the radius of this part, which is not the same as that. This is the slant height right there. Also there's the slant height. The radius is not on here, other than the fact that distance from here to here is 2 pi r, because it has to wrap around and fit there. Now, visually, if you put these two corners together, the middle part will pop up and give a height, and then the outside will then fit on top of this circle, which means the outside distance from here all the way around to this point is 2 pi r, because it has to fit on here. Okay, so again, this only has two surfaces. This one is simply pi r squared. This one, although not at all obvious, is pi r L. There's a derivation of this that I typically do in class, but it takes a while, and I'm not going to do it on a video. So if you want to figure out how that comes from, look in the book. They probably have it there, or look online. I think in the book they might even just state that. But there's a derivation of this which uses the sector areas that we did in the last chapter. Okay, so surface area of a cone is therefore pi r squared, my first surface, plus pi r L, my second surface. And that's it. Make sure you write that down. Now, what do we use cones for? Traffic cones, ice cream cones. There aren't too many things. Witches' hats. But not many things are really cones. It's not a hugely convenient shape except for those things I mentioned. Okay, now I'm going to erase this except for the picture, and we'll do some problems. So I'm going to give you the radius as 15 centimeters and the slant height as 25 centimeters. And I want you to try to find the surface area. So I'll pause the video there and try to calculate that. Okay, if you're back, surface area will be pi r squared, which is pi 15 squared, and the cone part of it will be pi r L, which is 15 times 25 in this case. This is 225. That I believe is 375, so this is a total of 600 pi, which is 1,885 rounded centimeters squared. So hopefully you got that. Okay, one more problem. This time, I'm actually going to give you the actual height. And this one I won't make you do on your own. I'm just going to show you how to do it. So instead of giving L, I'm going to give R, I'm going to call that 5 inches. And I'm going to say H this time is 10 inches. And I don't know L. Okay, so I need to find the surface area of this. I know part of it's pi 5 squared, the circle. The other part is pi 5 times L, but I have H. So how do I find L from H? The same way we did with the pyramid. Use the Pythagorean theorem. This is 5, this is 10. This is a right angle, so I can find the slant height here as L. And I'll start with L squared. L squared is simply 5 squared plus 10 squared, which is 125. That's not L, that's L squared. So L is radical 125, which in advanced geometry we could reduce this to 5 radical 5. So that goes over here. Radical 125 or 5 radical 5. I'm just going to put it in the calculator anyway, so it doesn't matter which of those I write down. So now I get 25 pi for the circle, and pi times 5 times radical 125. And that gives me 254.2. And what are my units? Inches squared. 0.16 really. Okay, and that's it. So that's it for cone. The only tricky part will be if you're given H and you have to find L from that in order to find the surface area. But other than that, it's, I think, pretty straightforward. Okay, let's go on to a sphere. This is the last shape we're going to do today. A sphere, I'm going to again write down the definition and the surface area eventually. So a sphere is again a 3D figure, not a polyhedron in any way. It's a 3D figure made up of points, a distance r from a single point. That sounds very much like the definition of a circle, and it is, except that it's 3D instead of 2D. So let me draw one. Typically draw an oval and then just draw an actual circle around it. It's a pretty round one. It's a little lumpy. There we go. Dot line that. And there's my sphere. So what I mean by the definition is that distance to there is r, and the definition to any point on that sphere is, in fact, r. Okay, what's the surface area of this? It is 4 pi r squared. It actually only has one surface. Usually the other ones I started by drawing a net, but you actually can't draw a net of a sphere. It doesn't have a net. For example, one of the uses of this is actually globes, like the Earth. It's not quite spherical, but for an approximation in this case, it's pretty close. If you try to flatten out the globe of the Earth and create a map, it is very difficult to do. And there's a whole, basically, mathematical science behind doing this, which you can go online and see. Probably you've seen like the Mercator projections and things like that, or you've seen ones that look like this. If you've ever seen these maps, you can go outside and find them like that. This is how they sometimes draw maps. The Mercator projection is a little different. It's kind of truncated out so the top is small. But none of these are actually accurate. They're all approximations and have various uses. This is actually pretty useless because if you just get like chunks of the Earth. But anyway, the point is you can't make a net out of a sphere. So I can't even do this in this case like I was doing the other ones. Now, where's this 4 pi r squared comes from? The pi r squared is the circle, so it kind of makes sense. It's circular. Where's the 4 come from, however? The only way you can do that is from calculus. So I'll show you how to do that in 2-3 years. For the moment, you just have to believe me it's 4. But logically, it makes sense that it's bigger than 2. If it were just a disk, the top would be pi r squared and the bottom would be pi r squared, and you have 2 pi r squared as the surface area. Think of it as like a coin. But it can't be 2 pi r squared because you're pulling it out this way. And that's what it actually turns out it goes to 4 if you do that. As I said, I'll wait till calculus so you can actually derive that. Okay, so that's it. That's my surface area. What do we use this for? As I mentioned, things like the globe itself. Also, anything that we store in spheres, mostly things we store in spheres are things like high pressure elements, like propane, for example. I used to have propellant tanks on spacecraft that used to look like this as well. The reason you store things in spheres is because it is the actual absolute optimum maximization of volume for a given surface area. So if you want to minimize the amount of weight for an object and store the most stuff in it, the sphere is the best shape. However, it's not very useful for storage mostly. You don't want to have your pantry filled with a bunch of cans of tomatoes in spheres, although it would be the cheapest way to do it. Things that so other things you see that are in high pressure, that's sometimes like, for example, propane tanks, scuba tanks have a look like this. That's weight, but it is also the fact that if you put pressure inside this thing, the circle actually is the optimum shape for storing pressure. Okay, so there's a couple examples for spheres. Also, maybe if you're making basketballs for a living. Now I'll do a couple problems. I'm going to just assign r to, 2 inches. What I want you to do is find the surface area of that sphere. I want you to pause there and calculate it. Okay, if you're back, this is 4 pi 2 squared. That's 4 times 4 is 16 pi. Calculate for that. 16 pi is 50.3, but I use the units, inches squared. Okay. That's it for spheres. Now I'm going to now summarize the formulas for all of the ones we've done. Make sure you've got a summary page somewhere in your notes. So we did cylinders. Actually, we did right cylinders, really, meaning it was always a right angle between the height and the base. Right cones, and spheres. And the surface area formulas for cylinders are 2 circles, pi r squared plus pi r squared, plus the rectangle part, 2 pi r h. Cones are pi r squared plus pi r L, where L is the slant height, and spheres are 4 pi r squared. Okay, there we go. There's the 3 surface area formulas. That is, last thing I'm going to do is put the homework down. So today's homework is for geometry. Here's a worksheet, which you should have in your email, on surface area of cylinders, cones, and spheres. And for advanced geo, do the worksheet as well. Plus, there are, I believe, 3 challenge problems. Page 715, 41 through 43, all. And then SAT problems 44 through 47 all also. All right, that's it for today's lesson. Thanks.